Section 5.2 is a section on inverse functions. So we're going to start from scratch here. We're going to talk about what an inverse relation is. We'll build our way up to inverse functions. Definition. For a relation defined by a collection of ordered pairs x comma y, the inverse is a role reversal of the inputs x and the outputs y. That is to say, then the inverse relation becomes the collection of ordered pairs y comma x. So let's take a look at this numerically. So one more thing, notation. For a given relationship, R, we denote the inverse, excuse me, the inverse relation as R with a little -1 up there. This is red, R inverse. So it doesn't mean the reciprocal. Excuse me, it means the inverse relationship. So numerically, if R is the collection of points -2, 1, -1, 3, 0, 1.
A little bit.
What's that? Scroll up. 0, 1, 1, 2, 2, 4. Then R inverse is the role reversal. So we're going to switch each one of these ordered pairs. 1, -2, 3, -1, 1, 0, 2, 1, 4, 2. The old switcheroo. And I'll leave that up there so a couple of you guys can catch up. Okay. Oops. Algebraically, if y is equal to, let's see, 3x plus 2 is the relation, then the inverse relation is a role reversal of x and y as above. So what we're going to get this time is then, we color code our x and our y is the same way. Whoops. Our x and our y is the same way. Then what we're going to get is the following. X is equal to 3 times y plus 2. So we took x and made it y, and we took y and we made it x. So this is the inverse relationship. Often, algebraically, we solve the inverse for y. So this would be something like x minus 2 is equal to 3y, or y is equal to 1/3 x minus 2. And we might leave it in this form and say that we say y equal to 3x plus 2 and y equal to 1/3 x minus 2 quantity are inverses. So those are inverse relationships. Okay. And we should note that they have the same properties as above. That is to say, we note if, let's see, when y is 1, sorry, when x is 1, y is 5, satisfies the above, y equals 3x plus 2, then 5, 1 should satisfy y equals 1/3 x minus 2. So we find that y is equal to 1/3 5 minus 2, which is 1/3 of 3, which is 1. Check. Yes. And so the spot checking it in one spot there shows that these at least hold for that particular ordered pair. So algebraically, numerically, we're both just switching the roles of x and y. That leads us finally to inverses graphically. So suppose we have a relationship, and it doesn't have to be a function. I'm going to duplicate this guy. Let's see. So let's see. I'm going to draw a silly function here. But not a function, a silly relationship. There it is. This is the relationship R. And really what it is it's a collection of ordered pairs. And so we might do something like treat this as a collection of ordered pairs. The scale here is kind of rough, but I'm just going to make up a scale. Let's see. If I call this -3, 0, then I should have done that better with some better ordered pairs there. Let me start this over. So I'll put an ordered pair there. I'll put an ordered pair here. I'll put an ordered pair here, here, and let's see, here, and here. And hopefully I can connect the dots. That's terrible. Why was it terrible? It's the first time I've ever tried to draw the points first. Let's do this. Maybe that's better. Blech. Anyway, you get the idea. There's some crazy function. I'm totally not in love with any of that. Let's go back to basics. And in the magic of editing, we're actually starting this. So let's talk about inverses graphically. And let's say I have a relationship that's silly, looks something like that. R is my relationship. And it goes through some ordered pairs. But the idea here is that for all of these ordered pairs, whatever they happen to be, maybe that one is 0, 3, and this one is 3, 4. And do we have any other good ones on there? Maybe that one is -3, 0. We're going to do a role reversal of some of those ordered pairs. So let's see here. What was 3, 0 is now 0, -3. So I'm reversing the ordered pairs. What was 0, 3 is now 3, 0. And then we have another one at 4, 3. And there were some other ones along the way. Let's see, this was -5, -2. So -2, -5. Something like that. This is going to be hard to draw, but it looks something like that. I know I left out some of those. But the idea here is there's a few ordered pairs that are never going to get changed. That is to say, in role reversals, some ordered pairs are fixed, like 0, 0, 1, 1, 2, 2, 3, 3, -4, -4. Any ordered pair where x equals y is fixed under the inverse operation. So what that means is, no, let's not use blue. If we take a look at the line y equals x, and we pick this graph up, although it's not going to look too great. Let's see if I can do this. It's supposed to look like a mirror image across that line. Obviously, I didn't draw it very well. So this means that y equals x is the axis of reflection, as they say, for inverses. So again, very quickly, if I have something like a curve R that looks like this, what I need to do is I need to draw the line y equals x. Use that as my axis of reflection and do my best to just mirror this. And that would be R inverse. I'm not sure if I labeled that up here. R inverse, R inverse. So that's the idea for inverses graphically.